Hey folks, welcome to this lesson on intermolecular forces. So what we've been doing right now is trying to figure out bond polarity and then figure out molecular polarity. And now we're going to look at is how do these things play together and what kind of forces exist between molecules. Now we spoke about intramolecular forces, so these are the forces between atoms in a molecule, such as covalent bonds and ionic bonds. Okay, so covalent bonds, and if we're talking about ionic crystal, we're talking about ionic bonds, and these are really, really strong, and they require a lot of energy to break. However, what we're going to be talking about now is our intermolecular forces. These are the attractive forces between molecules. So once again, we're going to be talking about covalent things primarily. And there's a couple here, lambda dispersion forces, dipole-dipole, ion dipole, and hydrogen bonds. So we're going to be talking about how these are created and the relative strengths with one another. Now, one thing to really keep in mind is that these intermolecular forces are quite weak when compared to the intramolecular bonds. So for example, in order to vaporize or to evaporate some water, we need to break some of our intermolecular forces, and that takes about 41 kilojoules. That doesn't really mean much in terms of a number to us right now, but look compared to 930 kilojoules, which was the amount of energy to break all the covalent bonds inside. So inter and intra, again, when we look at this water molecule, we can see we have different types of bonds. The bonds that are bonding the hydrogens to the oxygens to the hydrogens, these are intramolecular, and these are covalent in this case. And if we remember our electronegativities, which is going to be 3.5 minus 2.1, we're going to realize that these are polar covalent bonds. Now, when we look at the molecules themselves, this being a molecule here, this being a molecule here, there are some forces in between them that help them interact, and these are our intermolecular forces. So again, these are responsible for their physical properties, for example, their states, as well as some of their physical properties which we briefly spoke about before, and we're going to be talking about these a little bit later. Just a nice little side note is this beautiful diagram over here, and you can see that the water molecules, again, we've talked about how to figure out whether these bonds are polar or not, and then we figured out how to determine whether the molecule is polar or not. And if you remember, these bonds are polar, going to be towards oxygen, and the overall resulting dipole is towards oxygen here, and making this side of the molecule slightly negative, this side slightly positive. And now what we can see is that there are similar molecules, adjacent ones beside it, and the slightly negative sides interact with the slightly positive sides, and again, slightly positive sides interact with the slightly negative sides. So these are the intermolecular forces that we're going to be looking at. We're first going to start off with the London dispersion forces and move on to dipole-dipole. A little subsidiary of dipole-dipole is ion dipole. Obviously there's an ion involved there. And finally we're going to look at hydrogen bonds, which is a strong one, but not the strongest. The ion dipole one is usually considered the strongest one. Some, depending on what textbook you read, these two can be flipped over because you can see the high end is 40, the low end here is 40. So some of them are switched up a little bit. So London dispersion forces, these are the weakest forces, and they're a temporary attractive force. And it's all based on the movement of electrons. They create these temporary dipoles. Again, dipole, remember, there's going to be one side that's slightly negative and one side that is slightly positive. The electrons will be more to the negative side. And this is all based on the movement of electrons. Now, if we take a look at this argon atom here, again, this happens between atoms, in atoms and in molecules. And this argon atom, their electrons are mostly shared evenly on all sides. But as we know, if you see my pen moving really fast, these electrons keep moving. And if we take an instantaneous snapshot, we can maybe see sometimes that there are more electrons on one side than the other. And so that means that this side will be slightly negative compared to this side. So if they keep moving again, and we stop it, and again, maybe this side over here will have more negatives than this side, making this side slightly more negative than this side. So it's very, very instantaneous. It's all based on the movement of electrons, and as the electrons keep moving, these dipoles keep moving as well. And so here we see a kind of snapshot of what's happening. Here you can see a neon atom. Again, these happens between molecules and molecules, or between atoms and atoms. Anything that really has electrons has these London dispersion forces. So the key thing that you have to remember is that all molecules and all atoms have London dispersion forces. This is key. Okay, they're very, very weak forces. They're very, very weak, but they all have them because they all have electrons, and because they're made out of the movement of electrons, they all have London dispersion forces. So if we go back to this little photo over here, we can see that the electrons are pretty much even on both of these atoms. What we start seeing here is that on this side, there's started a collection of atoms. So this side is becoming slightly more negative, I'm just going to put a slightly there, slightly more negative and slightly more positive on that side. And what happens is that maybe this negative side will start moving on to here, pushing these electrons away from it. And you'll see that on both atoms, this side will be slightly negative compared to this side. Same with this side, slightly negative compared to this side. Now, because we have this positive side, and because we have this negative side, they're attracted to one another, and we get our London dispersion force. We can also create an induced dipole, so this can happen a number of ways. In this case, we have both nonpolar atoms or nonpolar molecules, whatever they want to represent, and maybe one of them starts developing a dipole. So again, all the electrons, this kind of blue area represents the electron density, and it's even here. But let's say in an instantaneous snapshot, all the electrons move on to this side over here, making this side slightly negative and this side slightly positive. So because this atom has all its electrons distributed evenly, well, the electrons are going to start getting attracted to this positive side. And if they start moving over onto this side, because they're attracted to this positive side, they themselves also develop a dipole. Now once they develop these dipoles, these electrons, as these ones move here, the electrons will also move here, and as these ones move over here, these ones will move over here, and they start creating this thing called an oscillation. And they create this kind of almost lattice, and this helps keep the molecules that have these dipoles together, and they cause them to stick together for a very short time until at least the electrons move again and reestablish a new dipole. Now, there are two things that affect the strength of the London dispersion forces, and here we can see the boiling points of two molecules, and they're very different from one another. In this case, we just have a simple methane, and we can see that it boils at negative 161 degrees. So it boils, it becomes a gas at a very, 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 very low temperature, which means that at room temperature, this would for sure be a gas. And we can see that the interaction is very, very small. The only place that they touch is right over here. And that's the only place where you can form these London dispersion forces. Now, if you look at the third one over here, we can see that they are much bigger. And bigger equals more electrons. More electrons equals more London dispersion forces. So what we do see is because they are bigger, they have a higher boiling point. They boil at plus 9.5 degrees Celsius. However, they're not the biggest one over here. So what's the difference? Well, if you look at these ones, both of these molecules, this one over here and this one over here, have the same amount of carbons. Okay? And the fundamental difference is that the way that they're shaped. This one on the right is more of a circular shape, while this one is more of a flat shape. Okay? The shape of the molecule is important because it increases the amount of surface area. More surface area means more points of contact, increased contact, and more contact means more London dispersion forces. Ultimately, if there are more London dispersion forces, you're going to require more energy to break them apart. This energy, it could be boiling point or melting point or whatever. The second type is dipole-dipole, and this is a little bit different because the way that this occurs is through a permanent dipole. So if we take a molecule here, for example, right there, we can see that it has this vector arrow pointing in this direction. Now, if you remember going back to polarity of molecules, how are these vector arrows established? Well, it's all established based on the difference in electronegativity. Okay, so what that means is that this atom over here in this molecule must have a larger electronegativity to pull the electrons onto this side, making this side slightly negative, this side slightly positive. Now, the electronegativity of an atom never changes. It's always the same for that type of atom. And so this is called a permanent dipole. Because the electronegativity will never change, the amount of pull of the electrons won't change, and the side that is slightly negative and slightly positive won't change. So it's all based on a permanent dipole through the electronegativity differences of atoms. And what you can start seeing is there's a certain attraction. So here, the negative side of the top molecule is attracted to the positive side of this top molecule, and the same thing here, negative to positive, positive to negative, etc., etc., etc. There is some repulsion, but that's not the key that we're going for right now. We're just looking at the attraction at the individual molecule. Again, we can induce a dipole. So again, a dipole is one side that's slightly negative and slightly positive. And let's start off with this molecule here. Here we have oxygen. Both same type of atoms. They have the same value for electronegativity. So this is going to be a nonpolar molecule. There's not one side that's more negative than the other. But if this molecule kind of approaches approaches a polar molecule. This is polar because this side is going to be slightly positive and slightly negative. We kind of already spoke about that. Because this side, the side of the water molecule, is much more negative, it's going to start repelling the electrons in this oxygen molecule. And if all the electrons are going to be starting to be repelled in this direction, where they're all going to land up on this left side. And this is exactly what we see. So most of the electrons are going to be moving on to this side of the molecule, which makes them, this side of the molecule, slightly more negative than this side of the molecule compared to where it was before. So this is called an induced dipole. It was induced by something else, and now this is a polar molecule. Okay? It has one side that is more negative than the other side, compared to where it was before, where it has no slight negatives or slightly positive. Now the cool thing is that if you remove this water molecule, it'll go back to normal and become this nonpolar molecule, which it naturally wants to tend to. The third type is ion dipole, and this is very simple. It's a polar molecule, something that has a slightly negative and slightly positive side. Slightly, and slightly. Interacting with something that has a full charge. So remember, something with a full plus or a full minus occurs through the transfer of electrons. Something with a slightly positive and slightly negative charge occurs through unequal sharing of electrons. So they're slightly different. And so in this case, when we look at sodium and whatever this polar molecule is, there's an attraction between the negative side and the positive ion. And here we have an anion, and it's attracted to this slightly positive side. The larger the charge, the stronger the attraction. And we'll see this as a big player when it comes to water being dissolved. Sodium being dissolved in water. So sodium is again made up of Na and Cl ions. And so the negative side of the water, these oxygens, which are electronegative, is attracted to the positive ion. And the positive sides of these are the hydrogens, your oxygens, and these are your white ones are your hydrogens. The hydrogens, which are slightly positive, are attracted to the negative ion. Our last type of intermolecular force is hydrogen bonding. And this is a strong dipole-dipole interaction. So the key word is that it's a dipole-dipole. Okay? It actually is based on a polar molecule. So we have two polar molecules interacting with one another. The difference is that it's very specific in how it interacts. It needs a slightly positive hydrogen atom. So in this case, we have water molecules. These are going to be our hydrogen atoms, and this is going to be our oxygen. I'm just going to draw that in black. There's our oxygen. These are your hydrogens. So we need a hydrogen atom interacting with the lone pairs of a highly electronegative atom like nitrogen, oxygen, and fluorine. Now, if you remember nitrogen has two lone pairs. So I'll draw this. It has two lone pairs, and it has three non-bonded electrons. If we look at oxygen and fluorine, so oxygen has 1, 2, 3, 4, 5, 6. So it actually has two unpaired and two lone pairs. So it's very, very negative. And fluorine is also incredibly negative because it has actually three pairs of lone electrons. It has the 1s, the 2, 3, and it has one unpaired electron. So this positive hydrogen that's formed over here is interacting with the lone pairs, these ones over here and this one over here when we're talking about oxygen, and that forms an attraction. And this is pretty strong. Now, when we see this in a graph, what we can see is this is going down the groups. So this is group 4, this is group 5, group 4, group 5, group 6, and group 7. And what you can see is that there's this huge amount of energy that's required to actually boil these off. Here we have H2O, HF, and H. These are the hydrides. But when we look at carbon, it doesn't have that same huge amount of energy. And remember that we have nitrogen in group 5, oxygen in group 6, and fluorine in group 7. These can form hydrogen bonds, which are much stronger than the ones that this carbon can create. Carbon can only create London dispersion forces. And so the hydrogen bonds are much stronger than the London dispersion forces, and because they're stronger, they require more energy. Okay? More energy equals a higher boiling point in this case. So here are just some summary slides. You can print these off on the slides that I give you in class, just looking at the relative strengths. So again, you still have your intermolecular forces being the weaker ones, and your intra, for example, your covalent, ionic, and metallic, being a lot more stronger. Your intermolecular forces are really the ones that are going to be determining the properties of some of your covalent structures. Again, a nice little summary, and your intramolecular summary. Thanks very much for watching. See you next time.